Kanekar, who is a senior professor and J.C. Bose Fellow, and currently the Dean of NCRA TIFR. Nissim is one of the world leading experts in radio astronomy and observational cosmology. He completed his MSc from Pune University and his PhD from NCRA in 2000. He did his postdoctoral at several prestigious, he obtained several prestigious fellowships, naming the few, the NOVA Fellowship at Kempten Institute and at the University of Groningen, and Jansky Fellow at NRAO, USA, and the Max Planck Fellowship in 2007 to 2009. In 2009, he joined NCRA, and his research spans a wide range of topics like cosmology and galaxy evolution. Some of his influential contributions are the variation of fundamental constants, such as the fine structure constant and the electron to proton mass ratios over cosmic time. He also led major efforts in the tracing the evolution of cold hydrogen gas in distant galaxies using GMRT. And he also received for his outstanding achievements, he received various awards. Again, naming the few, like one of the highest honor is the Shanti Swarup Bhatnagar Prize and the Infosys Prize. And also, it's really apt to have him. He received the Vainu Gold Medal. And he received the Swarna Jayanti Fellowship as well, Ramanujan Fellowship. And he's also a fellow of Indian Academy of Sciences. It's really a great pleasure to have him at IIA. And please join me in welcoming Professor Levi.
So I guess I can walk around happily, right? Yeah, good. I feel like a caged lion when I stand for a lecture.
Don't mic now.
Yeah. I can put it in the pocket, maybe. Thank you. Thank you to Smita and to Shivrani and to Annapurni. It's a pleasure to be here. And it's a pleasure for two reasons. One is that it's always nice to give a talk to an audience that contains a bunch of old friends. And it's kind of, slightly depressing to think that some of you have been my friends more for nearly 30 years. So I'm sorry, they're all very old. But the other reason that it's a pleasure to be here is that I'm too young, fortunately, to know Vainu Bapu. But, unfortunately, but I've heard a lot about him from Govind. And Vainu Bapu was a person for whom Govind had the highest regard. So, and I cannot think of anything that Govind said about Vainu Bapu which was not hugely respectful and affectionate. And so I would say that that increases my enthusiasm to give this lecture out of just regard for your founding director. So I'm very happy to be here. I'm going to be talking today about work that we've done with the GMRT using primarily the band 4 receivers to probe the atomic gas content of high-redshift galaxies in what are called the GMRT CATz surveys. As you can see, we are somewhat acronym challenged. And the bulk of the heavy lifting in this project was done by two outstanding students, Aditya Chaudhary, who did most of the first part, and then Balpreet Kaur. And other people who've been involved in this project are Jairam Chegulu, Shiv Sethi, and Dwarkanath, and Bardali Das. The other picture over here is Kitu, the queen of our cats, after whom the survey was named, and she's kind of helping us to point the telescope towards the cosmos field, one of our target fields. So some of the more perspicacious of you, sorry?
Trying to listen the online.
Oh God. I sound much better live, which is not saying much. I do sound much better live. So some of the more perspicacious of you will have noticed that I have one failing. Many of the more perspicacious will have noticed I have many failings, but I speak really fast. And I always remind myself to go slow at the start of a talk, and I always forget. So please wave a hand, throw a chalk, do something to attract my attention. I'll slow down if you like. The second thing...
that is not that.
Yeah, or log into your Zoom and go biz. The second thing I'd like to apologize for right at the start is that I intend to move this thing forward, failing miserably at. Ouch. Hello. Yes, thank you. Oh, great. Yeah. So I intend to follow Max Delbruck's advice to Alfred Hershey on how to give talks, which is that I intend to assume that you know nothing, but that at the end of this hour, you will know everything. So I will assume complete ignorance, but infinite intelligence. So I'm going to start by telling you what galaxies are, what our view of galaxies is today. And this has, of course, come from the work of a lot of people. So what do we think a galaxy is? A galaxy is basically a device, a box for converting gas into stars. But the picture of how a galaxy does this and what influences a galaxy in doing this has dramatically evolved over the last 30 or so years. And today we know, based on a lot of observations, the gas basically flows onto galaxies from the intergalactic medium via the circumgalactic medium of the galaxy. And the flows could be via streams, and that's the current picture, where the gas basically accretes onto the galaxy from these flows, if you like. It accretes on, passing through the circumgalactic medium or via the circumgalactic medium. The circumgalactic medium is mostly warm or hot ionized gas at temperatures of about 10 to the 4, 10 to the 5, 10 to the 6 Kelvin for a galaxy like the Milky Way. And we probe it using ultraviolet absorption lines, X-ray UV emission lines. And this is one of the most challenging things that there is today. We have information about galaxies via emission in the very local universe, via absorption at higher redshifts. But this is one of the big areas of research, say, over the last 2 decades. And gas flows in, and then it condenses out onto the disk of galaxies. And the CGM then condenses out and forms atomic hydrogen, H1, which is primary fuel for star formation, which is the focus of today's talk. And the main way, or the only way in some sense, that we study H1 in emission, or to get the content of galaxies, is by the 21 centimeter emission line. And that's going to be the focus of today's talk. The H1 now in the galaxy cools. So the H1 initially, when it accretes at a temperature of about 10 to the 4 Kelvin in the warm phase, it cools, usually via metal radiation. Metals are the term that chemically challenged astronomers use for everything above helium. And you wind up going down to a temperature of about a couple of 100 Kelvin. And that's the cold phase of H1. You have further cooling. The H1 cools and forms H2, molecular hydrogen. That's the next phase. And that's the proximate fuel for star formation. That's the thing that actually goes into stars. The molecular hydrogen clouds are not traceable directly via H2 lines. H2 is a homonuclear molecule. And so the primary tracer of a molecular gas is CO, carbon monoxide, rotational lines in the millimeter and submillimeter. And that's what has been done over the last, say, decade and a half or so with ALMA. And then the molecular hydrogen clouds collapse under their own gravity, they fragment, and they form stars. The stars live their happy lives, and the bigger ones go boom fairly soon, and they chuck stuff out, they chuck metals out, which of course results in more cooling of the gas, and hence more star formation, which is good news for forming stars. On the other hand, stars also drive winds out, and the starburst can actually kick gas out of the galaxy. And that can actually result in a cessation of star formation. So if you kick gas out, you don't form too many stars for a while. But this gas can then rain down ballistically back onto the galaxy, and it can actually bring gas from the circumgalactic medium onto the galaxy, back to the galaxy, on a faster rate than it might come in via the flow. So you can actually form more stars in the medium term, even though you've stopped star formation in the short term. What all of this is telling you is that the process of if you like, a galaxy's life is fairly complicated. It's got a bunch of these processes. It's got accretion to form atomic hydrogen. It's got cooling to form cold hydrogen, and then further to form molecular hydrogen. It's got fragmentation, gravitational collapse to form stars. It's got the timescales of stellar life. It's got stellar winds driving stuff out, chucking energy into the interstellar medium. It's got this ballistic dropping timescale. It's got the timescale in which you consume the gas in the galaxy. All of these are competing in the galaxy's life. And the galaxy's evolution will depend on this competition, right? And so what you would like to do, if you want to understand galaxy evolution, is to probe all these processes, not merely in today's universe, but from the highest redshifts down. And that's what I'll be telling you about today. So as I said, there's competition. The competition, the two things that I will be focusing on today are accretion timescales. How fast does gas rain down on the galaxy? Is it slow or is it fast? And this is often over the last, say, 20-ish years, talked of as what is called the hot mode of accretion, which is the traditional mode, if you like, and which is very slow. And this is because hot gas takes time. You have to cool the gas to bring it down onto the galaxy, or what is called the cold mode. In the hot mode, the gas basically falls into the CGM and then is heated to the virial temperature of the galaxy. And the trajectories are radial onto the galaxy, and it gets heated up to a temperature of 10 to the 4, 10 to the 5-ish Kelvin, and it takes time to cool. And that's the big issue. That's the reason that the accretion is slow. On the other hand, in the cold mode, gas actually flows along these streams. And when gas flows along streams, it doesn't virialize. It collapses onto the galaxy at a temperature of about 10,000 Kelvin, which is the temperature of the warm neutral medium. Therefore, you don't have the cooling problem. Therefore, this form of accretion, the cold mode, is much faster than the hot mode. And that is the dominant mode, we believe, at least certainly in the early universe and smaller galaxies. So we like to measure the accretion timescale of galaxies as a function of redshift. The second timescale is what are called the depletion timescales, the timescale on which gas is consumed by star formation. And that's simply the ratio of the mass in, say, molecular hydrogen to the star formation rate. This, as you can see, as dimensions of time, or the mass in atomic gas divided by the star formation rate. This gives you the molecular hydrogen depletion timescale. This gives you the atomic gas depletion timescale, how fast is the gas consumed. And you can immediately see that if the accretion timescale is much longer than the depletion timescales, you will take much longer to bring the gas in. The gas will be eaten up. There won't be any gas in the galaxy because the accretion timescale is longer. Therefore, star formation will stop. So this competition between accretion and gas consumption is what determines the evolution of the galaxy, And we'll talk about actually measuring these quantities out to high redshifts, which is a huge challenge. Depletion timescales are easy, accretion timescales are hard. So that's the broad picture I'd like you to start off with at least. So, I'm old enough to have lived at a time where actually it was a good time for us because radio astronomy was where we had the highest redshift galaxies. You found high redshift galaxies by using, ultra-C spectrum sources in the 90s. And we had the world record, the highest redshift, very proud of ourselves. And then we got wiped out. The optical folk just cleaned the floor with us. And the reason this happened was threefold. This happened because in the mid-90s, early to mid-90s, a bunch of massive optical telescopes came online. Keck, the VLTs, Subaru in the late 90s, Keck in the early 90s, HST came online. And that is wonderful. So you had optical and near-infrared telescopes, which were spectacular. Spitzer came online in the early 2000s. Wonderful. But the thing which also changed was not just the fact that you had great telescopes. What changed was that there was a cute new technique that came up. And there was a new strategy that came up. The strategy first was to actually, rather than say, okay, look, I'm going to observe my favorite object with my favorite telescope and learn a heck of a lot about that object. People realized that you actually needed, if you want to understand galaxy evolution, to observe the same region of the sky with the whole range of telescopes. So this notion of the deep fields came up. You identified regions of the sky and said, look, these are worth going and chasing after. And then you took your, all your telescopes and observed that region. And so now you had multi-wavelength information about the objects in that region. And that changed many things in our understanding. This was probably it made the biggest difference. The second thing was what is called the Lyman break technique. The reason that we had very few galaxies up to the early 90s at high redshifts above 3, was the fact that you needed to do spectroscopy to get a redshift. Spectroscopy, as most of you know far more than I do, is painful. It's painful because you need to put a godforsaken slit on every damn object. Unless you build an IFU, you need to get a spectrum for each galaxy separately. This is a pain, right? And this was the reason it was very hard. It was expensive to get it for a large number of objects, and hard to get observing time to do it. And of course, the telescopes are relatively small, so you need a lot of time per telescope. What people came up with in the mid-90s, first Raja Guha Thakurta and then Chuck Stidell took it on and really did it as an industry, was the Lyman break technique. What Raja realized, and Chuck later, was that there is this break in the spectrum of galaxies, which happens at the redshifted Lyman limit, 912.3 angstroms in the rest stream of the galaxy. So for example, at a redshift of 3, for example, there is a break in the spectrum of a galaxy at 912.3 times 1 plus 3. At 3,600 angstroms or so, there's a break. What this means is that the galaxy will be bright at wavelengths above the Lyman break, but at wavelengths below the Lyman break, the photons from the stars are going to be absorbed by the H1 in the galaxy and go into ionizing the gas. So you'll see a sharp break. So you will detect the galaxy at wavelengths above the break, and not below. Now, this is beautiful because you can just make images of a region of the sky, broadband images of a wide field, and look for objects with a break. That immediately tells you gives you a sample of galaxies, which are approximately a redshift of 3, 4, 5, depending on where the break is, which filter the break falls in between. Great news, right? So now suddenly you have this huge population of galaxies, thousands of galaxies, which were available for study, where you had the approximate redshift via the break. Obviously, these are not very accurate redshifts, but if you wanted accurate redshift, now you could go and follow up those galaxies. You won't waste your time with low redshift galaxies, getting spectra low redshift galaxies, which you would have done earlier. Now you knew these galaxies are roughly at redshifts of 3. Now, if I want to sample galaxies at redshift of 3, I take only the ones with the break such that the redshift is approximately 3. Great news. Today, we have thousands of galaxies out of redshifts of 6, tens of thousands, hundreds of redshifts larger than 8, and the same technique, but now shifted to the Gunn-Peterson break in the epoch of reionization, is used to find galaxies with the JWST at redshifts of 10, 12, 13, 14, 15, and so on. And now you can follow these up for spectroscopy. So this is wonderful. This gives you a quick way of getting the approximate redshift of a galaxy. Right? And this gave us large samples of galaxies, which now you could get information on. And that's been available for about 30 years. So what have we learned about galaxies in the last 30 years? If I had to show one figure, if you like, which is the punchline figure of what we have learned, it's this one. It's often called the Maddow-Lilly plot. It shows the star formation rate density of the universe in logarithmic units versus redshift. Right? So this is in log units. So minus 0.8 is an order of magnitude higher than minus 1.8. And what you see is that the star formation rate density, and these are all measurements. These are actually measurements from different techniques, each one of these. And there's lots of detail in this plot. If you have questions about it, feel free to ask. But I'm not going to go into the details of the measurements. The punchline and those black lines are not a fit. They're just to guide your eye. Those are just the data. The data are just sitting on these with a very small spread. The star formation activity of the universe rises from about redshifts of 8 to about redshifts of 3. And this is from a 2014 paper. So we have much more information now in the higher redshift end. Things have not changed very much over here. It rises by about an order of magnitude from a redshift of 8 to a redshift of 3. And we kind of understand this because, in the early universe, remember I said that cooling of gas happens via metal line radiation. There's not that many metals in galaxies very early on. There's not been that much of star formation at earlier times. So what's happening is that gas is falling into galaxies. And galaxies are forming stars at some level. As some of the stars go supernova, they get you metals back into the ISM. You have more cooling, you have more star formation. So this part we kind of understand in a hand-waving way. This part is where things become interesting. For some reason, from about redshifts of 3, maybe 4, to about redshifts of 1, the star formation activity of the universe went flat. And it's often called the epoch of cosmic noon. Astronomers are not good for titles, yeah.
Different color coded points.
Different measurements, different techniques, that's all. So there's radio, there's optical, there's NUV. The orange ones are Spitzer. So there's all kinds of measurements. Each of them is a separate measurement, pinning a large number of galaxies into one small redshift bin. Yeah.
The star formation is independent of the kind of galaxy.
So 90% of star formation in the universe happens in what are called main sequence galaxies. Again, a result that has come from these samples, which are galaxies which sit on the relation. The main sequence is basically a relation between star formation rate and stellar mass. And this relation basically is higher at higher redshifts and then declines with time, which is the same as this, which is saying that the star formation activity of the universe is coming down with time. So the bulk of these galaxies are main sequence galaxies. 5 to 10% of star formation at any given epoch comes from starburst galaxies. The bulk is main sequence. You can think of these as Milky Way-like galaxies, if you like. So in this epoch, something happens, and we don't quite know what. But that's when the star formation activity of the universe basically flattens out, plateaus out. And it stays roughly constant for about 2 to 3 billion years, right? Out to about redshifts of 1. It has to be some kind of a feedback effect. We don't quite know what exactly this is. Okay? This epoch is often called the epoch of galaxy assembly or the epoch of cosmic noon. About half the stars of the Milky Way were born in this epoch, between redshifts of 1 and 3. And then, from about redshift of 1, you see a precipitous decline. So over here, this is about minus 0.9, and here we are about minus 1.8 or so. So the star formation activity of the universe declines by an order of magnitude from a redshift of 1 to today. And this has been known for about 30 years, since 1997 or so, when the first version of this plot was made by Piero Madao and Simon Lilly separately. Why this happens has not been clear. So this is the reason I put question marks over here. We would like to understand the evolution of the star formation rate density of the universe. And of course, you'd also like to understand the evolution. Why does this happen? Why does this flattening happen over here? This part, as I said, we have a reasonable hand-waving understanding of. So obviously, if you want to understand star formation activity, you need to look at the fuel for star formation, which is the molecular gas and the atomic gas. I will not be talking about the molecular gas today, but over the last 15 or so years, since the advent of ALMA, we have actually learned a bunch about the molecular gas, with the caveat that the molecular gas surveys, because the field of view with telescopes like ALMA is very small. So we are still dominated by cosmic variance in terms of the number of galaxies on which we have information on the molecular gas is still small. And the number that we have, which are main sequence galaxies, normal galaxies, there's a bias towards the most starbursty galaxies, and the active galactic nuclei in terms of studies of ALMA. So we don't have as much information, anywhere near as much information as we would like on normal galaxies, main sequence galaxies. But the broad picture that they're getting is that similar kind of pattern in the molecular gas with much larger error bars, because cosmic variance is a big source of error. Yeah.
Question is about this measurement of the sigma.
Yeah.
Now there are several empirical relationships.
Sure.
Are you relying on that?
Oh, sure. Yeah. So, but the point which you should take away is that these have come from very different techniques, right? So as I said, the orange points are Spitzer. There are UV points, restrained UV. There are radio points. These give you completely different empirical relationships. The fact that they agree, give you consistent results, is telling you that you probably you shouldn't worry too much about this. At the highest redshift, then things are interesting. As you can see, the errors are large. Although even this is kind of, as I said, this is from 12 years ago now. Even these measurements have become much tighter. Earlier, these measurements were like the magenta points over here are all restrained UV. So you'd worry a little bit at least about dust extinction. People would argue that high redshift dust extinction is not so important. It probably is something of a correction factor to worry about. But now with GWST, we have much more information in this range. So the picture hasn't changed.
Part of the galaxy.
Oh, so you're mentioning the overall star formation rate. You're the integrated star formation rate. These are not resolved star formation rates. The overall star formation rates. With Spitzer, for example, you don't resolve the galaxy. You have blobs. So the point to be taken, I think the point to be taken is that a whole range of techniques give you consistent measurements, and that increases the confidence in these results. I would be very surprised if any of these, if this broad pattern were to be changed with observation in the next 30 years, which I would not have said 30 years ago. So I think this we are reasonably pakka about. Yeah.
So the upper limit is 0.109.
Yeah.
The value means that any galaxy at any point of time has not crossed.
No. So this is, remember, the star formation rate density.
Yeah.
So it's solar masses per year
Per
per megaparsec cubed.
Okay.
So what you're doing is that you're taking a volume averaged star formation rate
Yes.
over a large number of galaxies.
Yeah.
So there are galaxies which have 5,000 solar masses per year individually, but they are very few in number. And so then you're adding all of them together and saying, okay, divide by the volume, and that gives you this. So this is the volume average, and typically hundreds, if not thousands of galaxies have gone to each point. Yeah.
So having put these big question marks there, so what is the big surprise in this? Why is there a good reason to explain?
We don't have an answer for why this happens. I mean, what is the big surprise? We didn't have an answer. I'm going to give you the answer in this talk. and at some level, maybe it's not surprising. Maybe it's not. But we had no direct evidence for why this was. This was a question. It still is. We still don't have a reason why this is happening. And you can come up with hand-waving reasons, but which of them is the cause, we don't know. So, but yes. And yeah, I should have said this at the start. Feel free to ask questions. Yeah. So I'm going to tell you about H1, right? So that's a picture of NG6946, a really cute galaxy, called the Fireworks Galaxy. It has tons of supernovae in the last 100 years. That's the stars from the optical ground-based telescope image. And that's the H1 from the Westerbork Synthesis Radio Telescope from Renzo Boomsma's PhD. That's in the 21 centimeter line. And the point is like cute, which is often not appreciated, is that these two figures are to scale. The H1 is much bigger than the stars. Much. You can add a few muches to that, bigger. Right? In dwarf galaxies, you can add a few more muches. It's about 10 times bigger in diameter. In normal spirals, maybe 3 times bigger in diameter. So redshifts of 0, 21 centimeter emission line studies, single dishes, and mapping with interferometers have given us a lot of information about the atomic gas in galaxies. We have the H1 mass. We can measure that trivially, modulo the assumption that the 21 centimeter line is optically thin. We have the H1 size. And it turns out that the H1 diameter of a galaxy is proportional to its mass. One of the tightest correlations that we know in astronomy over 5 decades of H1 mass. The H1 depletion timescale is known, the ratio of the H1 mass to its transformation rate. We know the H1 mass function, how many galaxies there are of a given H1 mass per unit volume in different regions of the sky. We know how H1 depends on the galaxy type. There's more H1 in main sequence galaxy, disk galaxy like the Milky Way, than say in ellipticals. We know the H1 scaling relations, how the H1 content depends on the optical properties, the luminosity of the galaxy, the stellar mass of the galaxy, and other optical properties. We know how the H1 depends on the environment. That field that galaxies in clusters, disk galaxies in clusters, have much less H1 than disk galaxies in the field. We know the Tully-Fisher relation, the kinematics of H1, how that connects up to the luminosity. So we know a heck of a lot about the H1 properties in the local universe from about 75 years of observations. What do we know? Even if you go to a little bit farther here, redshifts of 0.5, it's embarrassing, right? Because today we have galaxies in the optical and the GWST and redshifts of 15. And we don't want high redshift here at 0.5. So what do we know about H1 redshifts of 0.5? And the answer is that until 2020, we didn't know a damn thing, right? And this was embarrassing, but there were reasons for this. The reason is simple. The reason is that the 21 centimeter line is a hyperfine line. It's a forbidden line, very low Einstein coefficient, very hard to detect. That's the problem. Even today, despite very deep surveys with the VLA, with MeerKAT, with GMRT, the highest redshift at which we have a detection in an individual galaxy today is 0.45. That's from Julia Bluebird's work with the VLA, with a 1,000-hour integration in the Chiles project. That's the state of the art today. So what are your options? Your options are to do ultra-deep surveys, thousands of our surveys with today's telescopes. That's one possibility. That will, of course, let you pick out the peak of the distribution, the most massive galaxies. And what you really want to know is the population. You're just identifying a handful of galaxy redshifts of 2. Yeah, you can thump your chest, but it's not telling you about galaxy evolution. It's telling you about a small number of galaxies. You could wait for the square kilometer array 1 mid to come along a decade from now. So we hope. It seems kind of boring, me at least. I have a life. Or you can go optical studies. It's a possibility. But if you want to learn about gas and galaxies, those are basically, they seem to be your options. About 25 years ago, folks realized that this was not the only approach. So it turns out that if you have these 3 conditions satisfied, you have a lot of galaxies within your field of view. So you have a radio telescope, let's say, like the GMRT, which has a primary beam, which is quite big. For the GMRT, for example, it's about 45 arc minutes at 650 megahertz. So let's say you have a lot of galaxies within your field of view, which is kind of a given. Let's say that their redshifts are within the frequency coverage, such that the 21 centimeter line is redshifted into your receiver coverage. That's also probably a given. There are enough galaxies in the sky, given the radio interferometer field of view. The next thing is harder. You want accurate optical positions. That's easy. An optical imaging thing will give you the positions fairly quickly. What you need is spectroscopic redshifts. That's hard. And you need them to 100 kilometers per second approximately. You'll see why in a second. So you need accurate spectroscopic redshifts. And suppose now, in addition to all of this, your radio telescope has a wide bandwidth, of course, high sensitivity. We all want high sensitivity, and a wide field of view at low frequencies. Wide field of view is not a problem usually at low frequencies. Sensitivity, yeah, GMRT, MeerKAT, both have high sensitivity. Wide bandwidth, harder. If you have all of these things, then if you can take all these galaxies, you know their redshifts accurately, such that you can now align the lines in their rest frame So you measured all their 21 centimeter emissions simultaneously with a single observation. You measured the 21 centimeter emission from all these galaxies. Each of them is individually not detected. It's buried in, the signal is buried in the noise. But you now align them because you know the redshift accurately. Remember, the velocity width of the line is about 300 kilometers per second, something like the Milky Way, which is why you need to know the redshift to about 100 kilometers per second, half to 1/3 the width of the line. If you align them well enough, and then average, that's what stacking is, the noise will go down with the square root of the number of galaxies, and you get the average signal. This was something that Martin Swan came up with for his PhD, and Jairam, Robert Brown, and Butler Burton came up with independently. And they demonstrated it, funnily enough, at very low redshifts, and to show that they designed an experiment which is too shallow to detect emission unless you stacked. So a cute approach. So that's the game, basically, right? The problem is you need a large bandwidth. So people tried this. Jairam actually led this along with Philip Law and Frank Briggs with the GMRT. And the problem was the narrow bandwidth. That meant that GMRT had a bandwidth of 32 megahertz for about 20 years or so. 30 megahertz is small in terms of redshift. So you could just cover a few galaxies in one shot. Shiv, Dwarka, and I tried this at redshifts. So these observations from Philip were at redshifts out to 0.35. We were shameless and we tried to push to redshifts of 1.3. And we had about 800 galaxies in 4 pointings, 250 per pointing, very small numbers. And we got upper limits, basically. And that's all that we had until about 7 or 8 years ago. Things changed in 2018 when the GMRT was upgraded. And the upgrade meant that we went into these wideband receivers and, more importantly, a 400 megahertz correlator. And we then had these 4 frequency bands. This band had not changed, 1000 to 1450 megahertz. These 3 bands were new, 550 to 850. Earlier, we were 560 or so to 650. 250 to 500. Earlier, we were about 300 to 360. And 125 to 250. Earlier, we had 2 bands, one of which was at 233 and one was at 150 or so, 10 megahertz each wide. Yeah.
Stacking these 20 centimeter lines, are you taking galaxies with similar redshifts or all the galaxies that comes
So that depends, right? If you suppose you have enough galaxies and your signal is strong enough, then you'll break up your sample. So suppose I have a very high signal noise ratio, then I'll take as small a redshift bin as possible. But if I don't have enough signal noise ratio, I'll do whatever I need to do to get the signal. If I average a large redshift range, then I'm giving you the average H1 mass of galaxies in that large redshift range. So the issue is just detecting it to begin with. Once you detect it, then you can play these games of breaking it up. And I'll talk about that in a bit.
You can't break up these bands in smaller.
No. But for example, this band, as you will see in a second, covers redshifts of 0.7 to 1.5. So that's a wide redshift range. So simultaneously, I will get galaxies with redshifts of 0.7 to 1.5 by just observing in this band. This band gives me redshifts of about 1.8 to about 4.5.
Break them in between, right?
I can. In principle, I can use smaller bandwidth, but why would I want to? I prefer to use a big bandwidth so that I cover all the galaxies.
Brighter galaxies, the number of galaxies with good signal, then you would tend to have a.
So if I have enough signal, then I will happily break it up. Remember, I'm doing spectroscopy of all these galaxies.
Yeah.
So I have all the information.
Right.
How I combine the information is up to me. And I'll show you what I mean in a second. So this was the thing that changed the field, basically. So that's what we decided to do. We basically chose, that's the Maddow plot again. And this is the sensitivity of the 3 GMRT receivers, band 5 in green, band 4 in red, band 3 in blue. They're about the same sensitivity. This is in 1000 times gain upon DCIS. And so what we started off with was a 350-hour survey of the graph strip, covering redshifts of 0.4, and that's over here in this plot of redshift. Then we moved to higher redshifts. We did a 510-hour survey of the 7 deep 2 fields, covering redshifts of 0.74 to 1.45. That's with the band 4 receivers. And that is this very interesting redshift range, covering the end of the epoch galaxy assembly and then going down the decline. So you can see this part and this part. We then did a 133-hour survey, 7-pointing survey of Cosmos, same redshift range. And now we're doing a 600-hour survey of Cosmos Web, same redshift range. And finally, we've done a 500-hour, 525-hour pointing, again of Cosmos, covering this redshift range, 1.8 to 3.3. And that's over here in redshift. We actually go further, but this is where we have redshifts right now. So these are three projects that we've been doing over the last, say, 8 years, let's say. Some of which are over, some of which are not over. And I'm going to tell you mostly about this project, the 510-hour survey of the deep two fields. If I have time at the end, I'll tell you about new results from Cosmos Web, and I'll tell you a little bit about the pushing to even higher redshift, 2.5 or so, this redshift range. So that's the plan right now. So the reason that we could do this, the problem, as I said, was that some kind soul has to give us redshifts. Redshifts are really, really, really hard. And the reason redshifts are hard is that, one, you have to do the spectroscopy, but you have to not just do the spectroscopy, you have to do the spectroscopy of a lot of galaxies in a small region of the sky, but big enough that it fills your interferometer beam. And radio telescopes have big beams, right? So if an optical person is doing this, he or she might just say, okay, fine, I'll take a big telescope and observe this region, and that region, that region, that region. There's no particular reason to take a large region over here. It turned out, by sheer coincidence, for no good reason that I have at least come across, Sandy Faber and Jeff Newman and Mike Davis and company did a deep two galaxy survey using the DMOS spectrograph and the KEC2 telescope in this pattern. So these are regions in the sky. These are three of the regions for the deep two survey. And I've put the GMRT primary beam, or Aditya has put the GMRT primary beam at 650 megahertz overlaid on this. And you can see that they are ridiculously well matched to the GMRT beam. And this is sheer accident. Of course, it's on accident. The reason I'm showing this to you is that they did it. If they hadn't done it, I wouldn't have shown it to you. So it's on accident, it's here. But this made life wonderful. And this covered exactly this redshift range. That was not a coincidence. It's not a coincidence because that redshift range is exciting for galaxy evolution. So they were interested in this also. The redshift accuracy was less than 62 kilometers per second, which is perfect for our nefarious goals, right? And these were the 7 pointings that we chose to do. And this gives a number of galaxies, about 2,000. So 1,900 over here and 2,500, 2,458 over here in each of these pointings that we did. So we had about roughly 16,000. Yeah, sorry. Beg your pardon. No, they can't be. So at least very unlikely. In fact, that's a very good question. And hold on to your horses. I'll show you something in a second. So, but there's about 2,000 galaxies in each pointing, right? So, and roughly about 16,000 galaxies in all. The bulk of these, by this selection, they were chosen to be R-band magnitude brighter than 24.1. It turns out at redshifts of 1, this corresponds to basically blue galaxies. These are blue main sequence galaxies. Wonderful. About 1,000 galaxies are red galaxies. About 1,000 have AGNs. The bulk of them are just common or garden star-forming galaxy at redshift of 1, right? So that makes them wonderful for our purposes. So we did the stack. And so after flagging, the usual array from a 3-letter word, RFI, we wound up with 11,419 blue main sequence galaxies in this redshift range. And 510 hours observing time. And I'll cut straight to the chase. That's what we saw. So that's the 7 sigma result. So this is a stack in the image plane. And so we basically we stacked subcubes. We extracted cubes around each of these galaxies to actually get a separate cube for each galaxy. We shifted that cube to the galaxy's rest frame, and then we stacked the subcubes. So now we effectively have an image of a hypothetical galaxy which has been averaged together. A spectral cube of a hypothetical galaxy. This is at a resolution of 90 kiloparsecs, and that's Firoza's question. So we did this first in the 2020 paper at a resolution of 60 kiloparsecs. And we said, great, life is good. It turned out that when we got higher sensitivity, that was a 4.5 sigma result, but we got higher sensitivity, we discovered that as we made the resolution coarser and coarser, we were picking up more and more H1. So then what we did was that we stacked at a bunch of resolutions, 60, 70, 80, 90, all the way up to 200 kiloparsecs. And then we chose the final resolution such that the H1 mass didn't increase. And that was 90 kiloparsecs. Okay, so that means that we are formally resolving these galaxies. Okay, so that's an interesting fact of whatever. I'll show you what that means in a second. That's the H1 mass. The average H1 mass with a set of galaxies, which have an average stellar mass of 10 to the 10 solar masses, is 1.4 times 10 to the 10 solar masses. Now, this is already a surprise, or it should be a surprise. Galaxies in the local universe have an H1 mass much lower than their stellar mass. Like the Milky Way, for example, has 5 times 10 to the 9 in H1, and about 6 times 10 to the 10 in stars, right? An order of magnitude less. this is roughly a factor of 3.5 higher than redshifts of 0 if you take galaxies in an identical M-star distribution, redshifts of 0. So much, much more gas-rich. The H1 depletion time scale, we also know the transformation rates for these galaxies. The depletion time scale is about 1.7 gigayears. In the local universe, the depletion time scale is about 5 to 6 gigayears for such galaxies. So it's much faster. The H1 is, there's much more H1, but it's being eaten up much faster. And the curious thing, which I still I'm having a hard time wrapping my head about, we could deconvolve. One of the funny things that some of you will notice, you see a 4 sigma feature. The contours start at 3 sigma. There's a 4 sigma feature over here. And you say, what the heck is a 4 sigma feature, right? There should not be a 4 sigma feature away from the center. We are stacking at the positions of these galaxies. That is the beam. You also see a 3 sigma feature up over here and a corresponding weaker feature over here. When you deconvolve, this actually becomes a 2.7 something sigma feature. What's happened is that the beam, the side lobes of the beam are actually sitting on top of a noise feature, and that's going up. I mean, it's beautiful. I mean, the idea that you can stack the beam is hard to believe. Anyway, what is interesting is that, yeah. Sorry? Oh, this is via Monte Carlo. You can do it via a number of ways. So as I said, we have the cube. So I can get the error from the noise on each plane of the cube. I can also get the error by doing a Monte Carlo stack where I'm misaligning the galaxies. And then I so the error is plotted over here in the spectrum. Here. And you can see the error is slightly higher in the line regions. And that's because we fit a second order baseline excluding those regions, which bumps up the noise in those regions. And so this has been done self-consistently via the Monte Carlo. They all give you errors which are very, very similar. No difference. What is interesting, and I'm still astonished at this, is that, as I said, the H1 size diameter relation in the local universe is well known. It's over 5 orders of magnitude in H1 mass and size. The deconvolved size of 55 kiloparsecs is exactly what you expect for the local universe for a galaxy of that mass. So it looks as though the size diameter relation is known by galaxies at redshifts of 1. And that's some kind of feedback mechanism clearly, and we don't know why this happened. I think it's really cute. So if we can actually map galaxies, that would be great fun. We're starting to answer the question now. This is a complete side issue, so I won't spend time on it. But the nice thing, and this comes to your question, we have a 7 sigma result over here, 7.something sigma result, right? So now we can think about breaking it up in bins. Because we can get 4 or 5 sigma results in multiple bins of any parameter you like, right? So the first thing we did when we saw this fast depletion time is that we said, hang on a minute, let's measure depletion time as a function of stellar mass. So as I said, the depletion time is the time scale on which H1 is consumed. So this is a plot now of depletion time scale in gigayears versus stellar mass. These points are for redshifts of 0 galaxies from the XCATz sample. And you can see that the depletion time is about 6-ish gigayears for the low mass galaxies and about 3-ish gigayears for the highest mass galaxies. And this is the molecular hydrogen depletion time in the local universe, less than a gigayear. What this tells you is that the H2 is consumed very fast. The H1 is basically sitting happily over there like a reservoir. And as long as you bring in H1 or timescale of a few gigayears, there's no problem. H2 dominates the timescales. You can bring in H1 slowly. There's no problem, right? Fine. So H1 is not a bottleneck for star formation at redshifts of 0. What is the situation at redshifts of 1? Those are our measurements. So here, we have binned the data in bins of stellar mass. So these are the 3 bins. The stellar mass distribution of these points is exactly the same as for these points. And you can see that in every one of the bins, the gas depletion time is lower. It's about 2-ish gigayears for stellar masses up to 10 to the 10, consistent from 10 to the 9, 10 to the 10. But for stellar masses above 10 to the 10, it's about 0.85 gigayears. And that is actually comparable to the H2 depletion timescale. Which means that the H1 in the highest stellar mass galaxies, which I should have mentioned, are the ones which dominate that drop in the star formation rate density. 85% of the drop in the star formation rate density from a redshift of 1.3 to about 0.9 comes from the highest stellar mass galaxies. Those galaxies have an H1 depletion timescale of less than a gigayear. So this stunned us. Now, this is very interesting because remember our redshift range is 0.7 to 1.5, right? That redshift range in time corresponds to about 2 gigayears. And I said the gas depletion time is a gigayear, less than a gigayear. Which means that if I break up my sample now into 2 redshift bins with the same stellar mass distribution, I should in principle see evolution between those 2 bins on a very short time scale, if this makes sense. We did that. And this is what we saw. So the orange curve over here is a stack for galaxies at redshifts of 1.25 to 1.45. The blue curve over here is 0.74 to 1.25. So stellar mass matched samples, they have the same stellar mass distribution, two different redshift bins. Average redshift here is 1.3, average redshift here is 1. And you can these are both more than 5 sigma detections, 5.5 sigma. You can visually see that there's much more H1 in the orange than in the blue. Just jumps out. If you convert that to H1 mass, that's what you see. So this is now the H1 mass of XCATz galaxies in the local universe. H1 mass at redshifts of 1, about a factor of 3-ish higher. But look at this one. This is the H1 mass of galaxy at redshifts of 1.3. It's about 3 times higher than at 1. So there is spectacular evolution happening from a redshift of 1.3 to 1 in the H1 content of galaxies. Let me emphasize again, this is stellar mass match sample. We don't know what's going on here. It's an observational fact. It is happening. And there are a number of very hand-wavy reasons I give you why this might happen, none of which really explains to me why it happens. I won't go into why, because it's an open question today. But there are a number of reasons why this could happen, but we don't have an answer as yet. But what we have is that the mass of galaxy redshifts of 1.3 appears to be higher by a factor of 3 than that redshift of 1. Stellar mass match sample. So this is an area which I think really needs much more work. Okay, the combination of both of these, the very short gas depletion time and the steep decline, what this tells you is that the decline in the star formation rate density, what's happening is that the reason there's this decline, there's just not enough accretion. H1 is not being brought in fast enough to balance the loss of H1 but in star formation. So that's the reason there's this sharp decline. And that's the reason the star formation rate is dropping beyond this epoch. So this combination, the combination of the two, is telling you that the reason for that drop in the star formation rate that you're mentioning is happening because of insufficient gas accretion onto the most massive galaxies. Yeah, sorry?
The last point.
The reason this is happening, remember, this is the most massive galaxy. Here, the gas depletion time is more than 2 gigayears. The short gas depletion time is the most massive galaxies. The reason that the drop in the star formation rate, the star formation rate density is dropping from a redshift of say 1.3 to a redshift of let's say 0.9 is insufficient gas accretion onto the most massive star forming galaxies. Those galaxies are the ones which dominate the drop in the star formation activity. Those galaxies are the ones which have this very short gas depletion time. And those are the ones which have.
But doesn't the process itself imply that it should be an exponential rate because it depends on the existing mass itself?
The process.
The star formation rate will depend on the mass. The mass is getting depleted.
Yeah.
So you would expect some dN by dt proportion to M.
You expect, well, it's much more complicated than that. So
No,
it's
so
there's cooling.
Of look back time. I'm talking.
No, that's not a complication. The complication is cooling. So it's not simply the mass; it's the conversion of mass into cold H1 and H2. So it's not as simple as simply the mass, but the fact the mass is the basic reservoir. If your mass drops, that's your problem. It's not easy, and I'll show you in a short while how we can get accretion rates. But hold on to your horses in that one. Rosa, your question.
By the electromagnetic bands, right?
No, this is the H1 mass. It's the mass in the 21 directly in the 21 centimeter line. It's the H1 mass, the atomic gas mass. That doesn't matter. I mean, that could be a cause for this, although I don't want to go over there, but that could be a cause. But this is simply saying that the H1 mass of the galaxies is much higher at redshifts of 1.3 than at 1. The reason for that is a good question. That we can, there are a bunch of reasons. We can talk about that later if you like. That's a huge digression. That's one of my possible answers. But there are a number of answers. So AGN activity, transition of cold mode to hot mode, the fact that dark energy is dominant. If I say any of these, roughly, if I say 5 of these, each of them will have 1/5 of you, should have 1/5 of you shouting at me. And I will join each one of you shouting at me again. Each of them has problems. It's very hard to explain this to a population. The dark energy can explain it for a population, but even that, the timescales are very short. So if this were happening at redshifts of 0.3, I would say, yeah, possibly. Redshifts of 1, you have to worry. So I would be wary about dark energy. Cold mode to hot mode, more likely. But even that, the whole population has to shift, and short time scale is not easy. So I think this is an open question. So, the reason I have lost a lot of hair is I'm scratching my head about this thing. Okay, moving on. So we can also now do the same binning, and we can measure the H1 scaling relations. This is cute. So now you can measure this. We measure the H1 mass in multiple stellar mass bins. I can measure the H1 mass in multiple blue magnitude bins, and I get scaling relations. So this is the plot of MH1, the MH1 M star relation, H1 mass versus stellar mass. That's in the local universe against stellar mass matched bins. These are our measurements. And what you see is that even at the lowest stellar masses, you basically have just shifted this curve up. So the orange thing is a fit to these points, the green is a fit to these points. The whole thing has gone up, the slope is the same, right? So all galaxies down to 10 to the 9 stellar mass are gas-rich at redshifts of 1. It's not just the highest mass galaxies. To be honest, I find scaling relations boring. They don't tell me a damn thing. You publish papers on them, but they don't tell you a damn thing. But what can you do with them? That can get interesting. Turns out that Nick Scoville came up with a really cute thing, which was that you could combine the hydrogen, the molecular hydrogen scaling relation with stellar mass and the main sequence, which is scaling relation of star formation rate and stellar mass, to get a very vague handle on the accretion rate. But of course, he didn't have H1 information. What we realized was that if you combine the H1 stellar mass relation, the H2 stellar mass relation, which is known from Linda Tacconi's Rainer Genzel's group, and the main sequence at 2 redshifts, and you make one assumption. These are all observational facts. You make one assumption that a galaxy evolves along the main sequence. So a galaxy is on the main sequence at some redshift, and it stays on the main sequence. It doesn't jump off the main sequence. Right? That's the one assumption we'll go into this. Now you can write a set of 3 equations where you have the final stellar mass is the initial stellar mass. So that's a stellar mass, the final redshift. This is the stellar mass is the initial redshift, plus an integral over the star formation rate over the interval between the redshifts with some fudge factor, which gives you the amount of gas chucked back into the ISM via stellar winds. You lose some mass, basically, by throwing gas back, right? So that you can write now is the initial stellar mass plus some alpha return times some average star formation rate times delta time. The final molecular gas mass is the initial molecular gas mass minus this quantity plus how much of gas you formed from the H1. So that's the average amount of molecular gas, the molecular gas formation rate times the same delta T. And the final atomic gas mass is the initial atomic gas mass minus the amount of stuff that's gone into molecules plus the amount that's accreted, where R accretion is the average gas accretion rate. So 3 fairly trivial equations. Of course, the accretion rate is the net accretion rate. It's the gas accreted minus the gas that's been kicked out by the galaxy. Similarly, you could say the molecular gas formation rate, it's the gas that formed minus the gas that's been kicked out. But now you have 3 equations. If I give you these relations for a given redshift, I can tell you for a given initial thing, I know this quantity, the final thing, because I have that relation. Then let's start with this. So over here, I have the final stellar mass, I have the initial stellar mass, I have the main sequence, I have the star formation rate main sequence. I can get R star formation. I can put that in this equation. I know the final molecular gas mass. I know the initial from the scaling relations. I can get R molecular. I can plug that over here. I know both of these. I can get R accretion. So I can actually measure or infer, if you like, the accretion rate, which is something that people have been trying to do for decades now, just with that one assumption that galaxies evolve along the main sequence. That's the one assumption that's gone over here. So that's what we did. Yeah.
The SFR will depend on MH1, MH2.
No, the SFR is an observed quantity. The SFR is you are measuring the SFR
But in time.
Yeah. So that's the main sequence. The main sequence evolves with time. So you have the main. That's the main sequence relation. So given the stellar mass, I know the SFR. That relation is tight. Given the stellar mass, I know all of these quantities at those 2 redshifts. If I have this scaling relation, that's the game. That's what we got. So this is now for a redshift of 1.3 to a redshift of 1. And this is from a redshift of 1 to a redshift of 0. And what's included over here, the blue curve is the average star formation rate as a function of stellar mass, initial stellar mass, final stellar mass, The orange curve is the average molecular gas formation rate from initial stellar mass to final stellar mass. And the green curve is the net gas accretion rate, infall minus outflow. And what should jump out at you from this is that the molecular gas formation rate and star formation rate actually are in remarkable agreement over the entire stellar mass range, except right at the top. The gas accretion rate is nearly zero in this redshift range. And for the highest stellar mass galaxies, it's actually negative. Gas is being chucked out of galaxies. So essentially, galaxies are almost not accreting at all in this redshift range on the average. Again, that's the reason that star formation rate density drops.
So,
Yeah.
So one name was, so what if there is no gas around you?
Then we see that there is gas around galaxies. And maybe there isn't. Maybe that's the issue. But actually, we do see from absorption studies, we do see gas around galaxies. So there is gas. What is that gas doing is the question. And we see gas at much higher redshifts. After redshifts of 5, we see gas around galaxies, H1 around galaxies by a damp Lyman alpha system. So there is gas. Why is that gas not falling on the galaxy is a good question, and not fast enough. And what you see at lower redshifts of 1 to 0 is very different. Here the star formation rate is high. Both the molecular gas formation rate and the accretion rate are low. And what you see is that the redshift average accretion rate is actually a few solar masses per year, which is similar to what you expect for the Milky Way. In fact, if we do this for Apurbo's work, from redshifts of 0.35 to 0, you get actually for the Milky Way mass galaxy, about roughly 10.8, 10.9, 10.7, 10.8 over here, you get a few solar masses per year. Completely consistent with what we see for the Milky Way today. So this tells you is that for this redshift range, accretion is basically very, very small. In the intermediate redshift range, both molecular gas formation and accretion are limiting the process. You're not forming enough molecular gas, and you're also not accreting enough. They both are less than the star formation rate.
One thing.
Yeah.
Some amount of net accretion.
Yes, yeah. More than that redshift. So there is a transition that's happening. And this is too wide a redshift range, so we'd love to break this down. That's another thing that we want to do. Okay, moving on. Another cute thing you can do with this is that, taking the same argument, I can now add together the amount of gas in H1, H2, and stars. And I will, of course, shamelessly ignore ionized gas and say that's the baryonic gas in the galaxy. Now I know the baryonic gas in a given galaxy at redshift of 1.3, and I can evolve that galaxy forward to redshifts of 1 and to redshifts of 0. And I can ask the question, what was the baryonic mass of a given galaxy? Now just one galaxy, at a redshift of 1.3 compared to 1 I can tell you how it evolves. So this is a plot where I'm plotting the baryonic mass at redshifts of 1.3 divided by the baryonic mass at redshifts of 0 for galaxies with this stellar mass at redshifts of 0. So the Milky Way is over here. So a value of 1 means that this galaxy, the galaxy over here, has all of its baryons in place at a redshift of 1.3. Everything was already there, and all you were doing afterwards was cycling it around. And what you see is that all the high mass galaxies basically had all the baryons in place, right? They were losing baryons from redshift of 1.3 to today. Even the Milky Way has 90% of its baryons in place at a redshift of 1.3. 9 billion years ago, the Milky Way had the bulk of its baryons in place. Everything after that is just recycling. It's local physics, it's not accretion. And that is very surprising, at least for me. Moving on. We also, as I said, did the MH1 MB relation. We stacked in 3 MB bins to measure this relation. And this was a bit of a surprise because we didn't see evolution. So the MH1 MB relation is the tightest relation in the local universe between the H1 mass and any optical quantity. And that's the blue curve over here. And these are our 3 measurements, and this is the green curve. It agrees within about 1.5 sigma with the blue curve. The fact that it's slightly flatter is a curiosity, and we're trying to get these errors down. It's consistent now, but we need to check whether, is there no evolution or is there evolution? And there are implications for this. But it turns out that in the heroic days of radio astronomy, before we had these wide field surveys like HIPAS and alpha and so on, Sanjay Rao and Frank Briggs came up with this cute trick where you can combine the MH1 MB relation with the B-band luminosity function to get the H1 mass function. The H1 mass function tells you how many galaxies there are at a given H1 mass. And we'd love to get the answer to this question. Right? We know this answer today in the local universe from alpha, HIPAS, and so on, blind surveys. We have no idea at high redshifts. So now we have the MH1 MB relation at redshifts of 1. We can do this. We have the B-band luminosity function or optical studies, and we did that. So the dashed curve over here is the local H1 mass function. This is the number of galaxies with a mass higher than MH1. So it's like an integral over the mass function. The blue curve over here is what we get at redshifts of 1. There are 10 times more galaxies with high H1 masses, more than 5 times 10 to the 10, at redshifts of 1 than redshifts of 0. The universe is just massively H1 rich at redshifts of 1. Right? So this was a surprise. And this suddenly woke us up to the fact that if there are so many high mass galaxies, maybe we can detect them individually. All the stuff about stacking gives you average properties. But I'd love to get kinematics of individual galaxies. I can look at what a galaxy looks like. Maybe we can actually detect these galaxies, the biggest galaxies with few 100-hour integration, 1,000-hour integrations, maybe. We don't need 10,000 hours with today's telescopes. So this was the question. Could we actually detect 21 centimeter emission from individual galaxies? So that's what we decided to try. Where we said that, okay, our goals are to detect this from individual galaxies and then do stacking based on morphology and environment. To get morphology, we wanted HST and JWST imaging, and that picked out the Cosmos Webb field. And again, by sheer chance, as luck would have it, that's the GMRT primary beam at 650 megahertz, and that's the Cosmos Webb field. Completely matches. Don't ask me why. So with a single GMRT, we said we'll do a single GMRT pointing, because it turns out with one pointing with about 600 hours, we expected by a Monte Carlo run to detect about something like between 5 and 40 galaxies at redshifts between 0.75 and 1.5. So this shows you one of the Monte Carlo runs, which has about 20-ish galaxies here. So the fill circles are detections based on the stellar masses that we have in Cosmos. So we shamelessly put in a 600-hour proposal about 3 years ago for Cosmos Webb. And the GTAC, which is slightly more sensible than we are, allocated us 300 hours to say, boss, please show you can get something sensible with this. Unfortunately, we were observing near solar maximum, so scintillation was a joy. Unfortunately, the Department of Telecommunications had just done the 5G allocations, and 5G was now in our band. So RFI was terrible, but with GMRT we can do stuff. So that's what we have gotten so far. We have a 4.2 sigma detection of stacked signal from the first 90 hours. And things look okay. We're losing a lot of data because of scintillation, but that's a detection in Cosmos. That's about a 4.5 sigma thing over here. The H1 mass is 1.3 times 10 to the 10 solar masses, a redshift of 1.08. And that's a Cosmos point on the same H1 mass stellar mass relation. Completely agrees with the deep 2 points. And these are selected completely differently. So this kind of says that different fields completely, different selection completely, and they all match up. So we think this will work. But we are right now still at 100 hours. We are in the middle of processing the remaining 300 hours. And the plan is to get the next 300 at the next deadline. With any luck, scintillation will have stopped. If any of you solar physicists are going to tell the sun to shut up for a bit, for a couple of years. Finally, moving on to redshifts of 2. Aditya is one of these tough characters who says, one is boring, we've detected stuff, so we should push to higher redshifts. And so we said, okay, why not use the band 3 receivers and push to redshifts of 2 to 3. And so the obvious field again was Cosmos. We had a bunch of redshifts, for 1,000 redshifts in this redshift range within the GMRT field of view. And the frequency range is 380 to 480 megahertz, which is, as you might imagine, tough. That shows the field of view, and that shows the number of galaxies in there. We currently have a non-detection. We have one of those classically tantalizing non-detections, which is like a 2 sigma blip at the right place, which again, there's a reason I'm going to ball very quickly. That's the upper limit that we get on the H1 mass. So it clearly is not very much above the value at 1.3. So galaxies, it's not that there was dramatic evolution from redshifts of 2.5 to 1.3 and similarly dramatic evolution. The evolution even from our current data is not as dramatic between 2.3 and 1.3. So of course, we are pushing hard to try to get that thing down, but we are completely limited right now by redshifts. We just need more redshifts. And so there are 2 surveys which are happening on Subaru and on the VLT, with the prime focus spectrograph on Subaru and the Moonrise spectrograph, the Moon spectrograph, the Moonrise survey on the VLT. And so we are basically waiting on the redshifts from these spectrographs. The cubes are all ready. The moment we have the redshifts, we can stack happily. And we should, we are reasonably confident because each of these surveys will give us 10,000-ish galaxies within the GMRT field of view. So we're fairly confident we get a detection as soon as they release this thing. But this is where we are right now. So I'm going to stop over here and leave you with a summary. I hope I've convinced you that we can finally detect 21 centimeter emission at high redshifts from the population of galaxies via stacking. And I think we have a shot now to detect individual galaxies. But the individual galaxies are still going to be the tip of the mass function. They're not going to be the typical galaxies. And stacking still has a role, even probably in the epochs of the SK, the SK1 mid. Because even at the SK1 mid, you will still pick out the most massive galaxies. You will still, if you want to probe the typical galaxy at any redshift, you probably will need to average the population. And the SK1, of course, will have a much bigger field of view than the GMRT, which is nice. We'll have more galaxies. The reason we think that the transformation rate density drops from a redshift of 1 to 0 is simply the lack of accretion of gas. There's not enough accretion to bring in enough gas to balance the gas consumption via transformation from a redshift of 1.3 to about 0.8 or so. And we think that based on the accretion rate measurements, where we basically find there's very little accretion happening, net accretion, we think that's reasonably pakka. We found something which I didn't mention to you, but which I think is also cute, that the mass of the atomic gas completely dominates the baryonic mass of galaxies at redshifts of 1.3. 70% of the gas is the atomic phase, 15% in the molecular phase, 15% in stars. That's exactly the opposite of what you see in today's universe. Right? So it's a very dramatic effect. H1 is where the action is at redshifts of 1.3. We have the first H1 scaling relations at redshifts of 1 now. So one can start telling the simulators that they are wrong. We have measurements of the average accretion rate, and we find that they're lower than the average transformation rate at redshifts of 1 for all stellar masses. And one thing which I still am pretty zapped about is that essentially most galaxies seem to have, most of the big galaxies have most of the baryons in place at redshift of 1.3. I'm still a bit surprised at this. I mean, I would have thought the accretion would happen over a much longer period, and that's not the case. We have the mass function at redshifts of 1. There's far more H1 massive galaxies at redshifts of 1 than redshifts of 0. The bunch of questions that we still have, we have a lot of questions. I mentioned a few. One thing that I still am puzzled about is what exactly is happening at redshifts of 0.7, less than 0.7, because from the GMRT survey at redshift of 0.35, we're finding not much evolution from 0.35 to 0. That's also been seen by the Chile survey. So there is some tension. I mean, it looks as though there's a lot of evolution from redshifts of 1 to 0.3, 0.4, and not much beyond that. That's a curiosity. So we need to get that cleaned. The reason I'm not confident of the reason I haven't shown you the GMRT results is because, I mean, I'm confident of the result, but the implications are less confident of, because the problem is that you need to have a big enough cosmic volume. Otherwise, you're limited by cosmic variance. The cosmic volume that you need to get to an error which is less than 10% is about 10 to the 7 co-moving megaparsec cubed. For the Deep 2 surveys and the Cosmos survey, we are at about 10 to the 7. So we don't think cosmic variance is a problem at all. And that's the reason that you saw Cosmos matches Deep 2. For the GMRT survey in the Groth strip at redshift of 0.35, our volume is about 10 to the 5 co-moving megaparsec cubed. The Chile survey is about a few times 10 to the 5. So all of these are small. The redshift range is small, and the beam is smaller also, both of which should reduce the cosmic volume. So we need to get a much better cosmic volume, which will come with the CATz surveys, before we can make a definitive statement of what's going on at low redshifts. So finally, that action actually is at low redshifts over here. We think that we have a shot at individual detection redshifts of 1. We think we can get the average property of redshifts of 2.5. And we have a bunch of crazy, cute 4 sigma results, which are driving me completely insane. We have evidence for outflows from these galaxies by comparing the stacked 21 centimeter emission and the O2 lines, the oxygen, the single ionized oxygen 3727 angstrom lines. We see a beautiful offset between them, which indicates that the O2 is coming from outflowing gas in the stack in the 510 hours in the Deep 2. We have evidence that if you break up the stacked emission based on the velocity width of the O2 lines, the 21 centimeter emission for the narrow O2 emitters is really narrow. It's about 50 kilometers per second wide. And that is scary, because the only way in which you can get such narrow lines is if you have face-on disks. So we are petrified by this. It's about a 4.5-ish sigma result, little close to 5 sigma. So, but we don't want to publish this unless we are sure. So that's why we've taken a 580-hour run we've taken these data already. And the idea is that we will now nail this thing. We get to a 7-ish sigma and be absolutely sure about this before publishing. But that's open areas. We also want to, as I said, to get the dependence on the environment. All these will come with the data that we already have. So I'll leave you with that. Thank you.
It's a very interesting talk and very exciting results. Questions?
Yes, couple of questions. One is, if you just show us that model.
Sure. gosh, long way back.
My question
Okay,
is
that's
about
fine.
the linearity of these.
It's not linear. It's not, as I said, these are not meant to be a fit. These are to guide your eye. These are not meant to be a fit. In fact, if you look at the
No, but it
Madhav
still
Dickens,
looks, I mean,
yeah, I mean, but be wary about what. So, in fact, if you look at the Madhav Dickinson paper, they fitted a curve to this, and they show a peak over
it's a
here.
universal, I mean, it's.
Yeah, but I mean, I wouldn't take those curves very seriously. I think if you look at the errors over here, right, this is the spread over here. And so therefore, I would certainly not say this is perfectly flat. It's consistent with being flat. Each measurement comes with errors.
Okay, let
So
me
therefore,
ask
I would be
a question.
wary about
Let me
straight
ask you
lines.
something else. What I could see, if you go back to that main sequence relation.
Yeah.
That's a purely empirical result.
Yeah, all these are empirical. All these relations are empirical.
Correct.
Yeah.
If you go to that result, that itself, by the set of equations that you just wrote below that, this next, why can't you actually predict the main sequence relationship? Keeping in mind MH1, MH2.
So there is a catch. So the reason that's kind of a chicken and egg thing is that those equations assume galaxies evolve on the main sequence. So to predict the main sequence evolution, exactly. So therefore you can't
write the
exactly.
But what
if you didn't have that assumption, you couldn't write those equations down.
Correct. But if you could impose certain things on those equations, then predict.
It's not easy to do it because see the thing is that I don't think you can invert that process. The number of unknowns is too high. The main sequence relation gives you this from this, right? So you don't have information, for example, about the accretion rate. So I need a measurement which will actually tell me this. I need a measurement to actually tell me this. I need a measurement to tell me this.
So you're trying to extract accretion rate from this.
Exactly. So now, if you could give me all the things that I'm measuring.
That obviously depends on the details of the physical. Right?
No, forget the details of the physical model. I'm just saying I want to measure the accretion rate. Forget about the details of the physical model. If I knew the accretion rate, if I knew theoretically the accretion rate, the star formation rate, and the molecular gas formation rate, I can then predict the main sequence. I don't have any of these. I mean, that's the problem. Our understanding of the physics is way limited at this point, theoretically.
I'm curious and surprised to say that there is a certain main sequence between the
that we know, yes. Yeah.
That is, if somebody can solve that problem.
There have been arguments at least which suggest, I mean, there have been arguments. We can talk about that in more detail later. Yeah, especially because there are more questions. Star formation rate density.
Star rate density.
Yeah.
See, star formation rate tends to get enhanced with directly.
Yes.
So does it also say that you have fewer galaxies?
Okay, so that's a good question, and it's a place which has caused a lot of the thing which is important to remember is that the bulk of star formation activity, the bulk of the star formation rate density is coming from main sequence. Those are not major mergers. Those are minor mergers. Starbursts are major mergers. Starbursts contribute 5-ish%, maybe more at redshifts of 2, but less than 10% at all redshifts. Which means major mergers don't play an important role in any of this. Minor mergers, yes. That's completely okay. But they will bump you off the main sequence a bit. That's not an error. So the horizontal thing is just the stellar mass range. So basically, the fact that this thing is the same as this thing is saying that they have the same stellar mass distribution. So the range is simply 90%, showing the 90% of the full range corresponding to that point. So therefore, they are exactly the same by definition. It's not an error, it's a range. No, I have no. I mean, I should be a little wary about this. There are two things. One is that this upper limit one should treat with a little bit of caution, and there are subtle reasons for this. The big subtle reason is that there are few redshifts, only 1,000 galaxies. But the most important problem is that these redshifts come from laminar alpha emission. Lyman alpha is a resonantly scattered line, which means that when you measure redshift Lyman alpha, you have intrinsic errors because the peak of the redshift that you get could be shifted because of dust obscuration. So we've actually measured this. So for these galaxies, which are the MOSTEF galaxies, there were 200 of them, we can compare the redshifts from Lyman alpha and the redshifts from the optical lines. MOSTEF is a near-infrared spectrograph. And what we found was that the 1 sigma error on the Lyman alpha redshift is about 230 kilometers per second. And that's on measurement. That is simply the intrinsic, the Lyman alpha shape is giving us a problem, right? This means that the alignment that you will get with the Lyman alpha redshifts, which dominate our sample, they are about 800 Lyman alpha redshifts, those redshifts are going to be less well aligned. So I will get a scatter in the width of, a spread in the width of the line just because of that. Now, this is a problem. So therefore, one should be very wary in such limits because the limit depends on the assumed velocity width of the line. If you assume a bigger width, you get a higher limit. Here we've assumed that the velocity width is the same as these lines. That probably is not correct because the Lyman alpha 1 sigma error is much larger than the error over here. So therefore, the width is probably going to be 500, 600 kilometers per second. So you might be able to take this thing up without any problems by maybe a factor of 1.5, 1.7, square root of this ratio. So I would be very wary about drawing any deep conclusions, even about this point. If you ask me about higher redshifts, I will say, boss, I want to go and observe. We don't know. That's the truth. I mean, if you had told people that these were the H1 masses at this range 5 years ago, they would have said, no chance in hell. So this is really what the universe is like. We don't know what the universe is like in redshifts of 2.5 even.
The star formation
That's a good question. I would say it's not clear. So, okay, it's possible. So I think it's an interesting question. So basically what you're saying is that, let's say the star formation rate, the star formation rate with stellar mass, there is cosmic downsizing. What this means is that the main sequence shifts to higher values at higher redshifts, right? This is effectively what you are seeing over here. So what I would love to do is to make a similar plot at higher and higher redshifts. And if what you're saying is right, that you will keep shifting upwards. That's what one would hope to see. The question is, at what point will that stop? Because as I said, there is an accretion effect that's happening also, right? So at some point, there has to be a balance at some point in galaxy formation. So we don't know the answer. That's one of the open questions I would say in the field right now. So we'd like to see what happens. So pushing this to redshifts of 4 would be a great deal of fun and would be hugely challenging. But we were doing it over the next decade or so.
I had 2 questions. One is you had shown the previous plot of the selection of galaxy versus recent result upper limit you had.
Yes.
So the AI. Yeah,
Sorry.
this one. So you have only the MOSTEF, the redshift values are only for a handful of.
Yeah, 200 from MOSTEF and about 1,000 from Z Cosmos D. Total number is 993.
If it is available, or I'm asking, is there any influence of galaxies which are there, but you don't know the redshift?
Yeah.
That might be.
So those won't affect our averages are only for these 1,000 galaxies.
Yeah, but you don't know if any other object is sitting in the field and bit contributing.
Okay, so I can answer in 2 ways. One is that could there be an object? Could there be a companion galaxy very close to this one?
Yeah, I mean, these detections are optical, right?
Yeah.
They may be optically faint galaxies.
Exactly.
But
yeah.
there could be
Yeah.
H1 rich galaxies.
Exactly.
There,
Yeah.
for
So
which you don't really see them,
Yeah.
but they are present.
Yeah.
And what will be such galaxies affecting your estimation?
yeah, so there's 2 ways of answering that. One is that we look for companions, really close by. We don't see, and there are optical images, very deep images in cosmos. We don't see too many galaxies having a very close companion. Our beam over here is about 70 or so kiloparsecs. Now, we don't expect confusion. So this is basically what is called source confusion. That there are 2 galaxies within your spectral resolution and within
I'm
your...
also going beyond source confusion. There could be something.
So anything beyond source confusion will not hurt us because we have enough resolution to separate galaxies out. So we can separate galaxies spatially and in velocity. So if let's say that I have a galaxy over here.
Them, there's no information about them in that field.
But then they don't contribute. I'm not averaging those.
Okay.
The ones which can contribute are the ones which I'm somehow including in my mass estimate because they are within the beam that I'm taking these beams and then stacking the beams together.
Yeah.
If there's a galaxy over here, I don't include it. I can't include it. So then it doesn't affect me. If there is a galaxy which I don't know about, exactly. So if there is confusion, then I could be hit. There we don't see direct evidence. In B2, we tried doing this. We actually excluded galaxies which were confused. It didn't make any difference. It's a small number of galaxies.
So you're also measuring H1 emission and H1 absorption.
So this is all H1 emission only.
Emission.
We separately do absorption, and there we have some cute results, but that's completely different.
But you have to act on also.
No, so the H1 absorption is only happening against radio loud objects. So in fact, what we have, the radio loud objects are AGNs, reactive galactic nuclei. We actually have excluded AGNs from our emission sample because the AGN can actually affect the H1 content of the galaxy. The AGN can actually drive winds and so on. It can kick the gas out or ionize the gas. So we have actually explicitly excluded any galaxy.
H1 emissions are
Exactly, only main sequence galaxies, no AGNs, no red galaxies. So in fact, that's another thing we'd love to do with the new run. We'd like to stack the AGNs, the galaxies which are AGNs, and see whether they have a higher or lower, we expect lower, whether they have a lower H1 content than the main sequence galaxies. But that we have about 1,000 galaxies which have AGNs so far.
Since you mentioned insufficient accretion from this medium, I was wondering whether you control for the environment of the galaxies it uses back.
Yeah, that's a very good question. So the answer is yes and no, as usual. That's what all good answers. The issue is that with the deep 2, right, we don't have the quality of imaging that we have is not that good. The optical imaging, we have great spectroscopy. We don't have that good HST. We have no HST imaging for most of the fields, right? So now, how do we get information about companions, about environment? So what we did was that there are papers which have looked at deep 2 and have done a Voronoi Delaunay tessellation using galaxies with redshifts. And now what we can do is that we can take galaxies which are in pairs and galaxies which are not in pairs and stack them separately. We've done that. And that is one of the results that I showed you, as I mentioned at the end. That's one of the tentative things that we're seeing. We are seeing the exact opposite of what you see in the local universe. In the local universe, galaxies in groups have less H1 at the same stellar mass than galaxies in the field. At redshifts of 1, at 4-ish sigma, galaxies in pairs actually have more H1 than galaxies which are not in pairs. And that actually is interestingly similar to what has been seen in the CO in galaxies in clusters. So this is something that we are very interested in, and I don't have an answer. What we're also doing now is that Joe Burchett has this cute way of getting the density field. So this thing is brain dead, right? It's simply saying that I have these redshifts. These galaxies are within some delta Z and some delta space, and they're in pairs, and that's it. Burchett has a way of getting the density field by using these slime models, where you can basically, put galaxies on these curves in redshift and space, right? And you can say that, okay, this region is higher density, this region is lower density. Now you can stack based on the large scale density, not just the local density. That is interesting. We haven't done that as yet, but that's something which we're trying to do now.
So we are seeing that within redshift of 1.3, there is not just extraponential rate evolution.
No, there is huge.
Yeah.
Hang on. Let's see if I have a plot. Yeah, here. So this is a plot of the evolution of the Staffmation of the main sequence. Staffmation rate was stellar mass as a function of look back time. And so this is the local universe, and it just keeps going up. There's huge evolution. Staffmation rate is a factor of 10 higher at redshifts of 1, and then it keeps increasing as you go to higher redshifts.
But between 1 to 3,
Oh, I see. No, it's not Staffmation rate. It's Staffmation rate density. Yeah, that's really important. Yeah. So density is yeah. Okay. Sorry. Please go ahead. Yeah. Yeah.
So my question is that in your study, in this Kavya.
Sorry, which one? This one?
Yes.
Yeah.
Here also, you see that for the redshift, really it is working, but within 1.2 to 1, you do not see that the mass is higher for the galaxies. So can all these things be connected, and we can tell that okay, this agent peaking in agent activity and the star formation rate being modulated by that thing. Can that be a reason behind this thing?
Yeah, so that's a good point. The AGN feedback has been one of the things that people have proposed.
Yeah.
Which one is the thing is a good question. Stellar feedback or AGN feedback. And AGN feedback probably dominates the high mass end, stellar feedback the low mass end
Yes.
for flattening. Right? This has been proposed. We don't have clear evidence for it one way or the other, but this has been proposed. In this thing, that AGN feedback is one of the possibilities that we are, I mentioned there are half a dozen possibilities, and half a dozen of groups in this room will kill me if I mention any of them. AGN feedback is one of them. But there are caveats. One big caveat is that we have explicitly removed all galaxies which have known AGNs, which means we have thrown away any galaxy which has a radio source brighter than 2 times 10 to the 20 watts per hertz. So that's one thing we've done already. We've thrown away any galaxy which has optical lines which are AGN-like. That's another thing we've done. Any X-ray galaxy, all of these have been removed. Which means that for AGNs to contribute to this, they have to be buried AGNs. Now, this is more scary. So if you have a large population of buried AGNs at redshifts of 1.0, it's possible.
Yes.
But that's a scary-ish thing. So there are, all of the solutions leave you feeling very uncomfortable.
I was thinking that the range is huge enough that the agent phase is already being evolved over that time. Because agent phase time is little bit like quite smaller than
Yeah, so the argument for the AGN contributing is basically this, but there's a catch. The catch is that, remember, these are averaged over thousands of galaxies. All of them now have to be in that AGN phase in a very short period of time. That is much harder. An individual galaxy has a short AGN phase, but there's no reason why the AGN phases should be all nicely aligned. And that is the problem that which people will kill me or I will kill myself for. The same thing exactly applies to, if you look at the cold mode. My favorite explanation for this is cold mode to hot mode transition. So that basically galaxies with high stellar masses, if you look at the highest stellar mass galaxies, more than 10 to the 10 solar masses, and ask the question, what is their halo mass? You will wind up with a number which is like 10 to the 12, maybe 7 times 10 to the 11, right? Solar masses. That is the exact mass at which we expect transition from hot mode accretion to cold mode accretion. Cold mode to hot mode accretion at that redshift. Redshifts of 1.3 or 1.4 or so, right? Now, the moment you shift to hot mode accretion, the accretion timescales are much longer, which means that this could explain it. You can shift from a fast accretion to slow accretion. That would slow down the fall of gas, and you're done. Same problem comes up. Why would an entire population behave in the same nice coordinated way? But that at least there is some hand-waving thing that galaxies of a mass will behave in some way, but it leaves me uncomfortable. There are other arguments. There is this, Claude André for Ship Giguere, when I gave this talk at a meeting, he got all excited because they've been finding that turbulence changes its behavior. Turbulence in the CGM changes its behavior as a function of redshift. So he was jumping up and down saying that maybe the CGM becomes supersonic at redshifts of 1.5, which is a very short time scale process. And that could completely change the accretion time scale. And so he went back to his fire simulations to check whether turbulence indeed becomes supersonic. And it does get more and more supersonic as time goes by, but it doesn't become fully supersonic and not at that redshift range. So all of these are uncomfortable things, which, a solution should finally make you feel a little comfortable you've understood something. I don't feel I have understood why that drop happens. And I think that's a place where we really need more data. We would like, for example, I would love to have a bin between 1.3 and, I'd like to have a higher similar ratio measurement, first of all. I'd like to be able to separate galaxies with different bins. I'd like to actually go and, for example, get X-ray continuum imaging and do a stack in the X-ray to check whether are they buried AGNs. All of these things would be fun. HST imaging would be fun, although nobody will give us that much of HST time to do a wide field thing, to look for point sources. Do these have more point sources? But these are all things that are worth doing. Some of these will be possible with Cosmos, because Cosmos has great X-ray imaging, has great JWST and HST imaging. So that's one reason to do it in Cosmos. Cosmos, weirdly enough, has crap spectroscopy right now. It will have very good spectroscopy. That's the reason we didn't choose it to begin with. Deep2 has much better spectroscopy. Cosmos has very poor mediocre spectroscopy, which will improve in the next couple of years. So we should be able to answer some of these in a direct way in the next couple of years. So watch this space.
In the interest of time, we should stop and maybe you can discuss over tea, or also like maybe tomorrow till afternoon around 11 is around. So please catch me.
So now I just would like to thank Professor Kanekar for sharing exciting science with us. I now invite Professor Annapurni to honor our speaker by handing over the mic.
That's beautiful. That's really lovely.
Please join us for IIA lunch.
And I'm sorry for shooting way over time, but it's entirely Arun's fault for asking so many questions in the talk.
Not me.
Your fault. I need to find one person to blame.
So, Nissim,
Yeah.
the other simulations